A comparison of classical machine learning, quantum machine learning, and hybrid models, illustrated using the example of binary classification of quantum states. Hi, this is me. I'm Elisabetta and a student at Northwestern, and today I'm going to present you my machine learning project. The project explores the differences of quantum machine learning and classical machine learning and compares both. Also, it illustrates the principle of hybrid models using the example of binary classification of quantum states. Quantum machine learning and classical machine learning can be compared based on a variety of measures. The chosen criteria in this project are the underlying data, the types of registers, the operating gates, the computing power, and the frameworks available to the public. Data in classical machine learning is stored using bits. Bits can either be 1 or 0, respectively on or off. There are two possible exclusive states that are measured deterministically. In quantum machine learning, however, the data is stored in so-called qubits. A qubit is a two-dimensional quantum state that can be 0 or 1 simultaneously. As the data has distinct types, it is stored in different registers. The principle is similar, nevertheless. Classical registers are n-dimensional arrays of flip-flops, circuits with two stable states that can be used to store binary data, while quantum data is stored in n-dimensional arrays of qubits. The operating gates that can modify bits or qubits vary as well. While classical gates are constructed from transistors, quantum mechanical gates are unitary matrices. Both types of gates are used to modify data but have completely different underlying operating principles. The computation power scales linearly with the number of bits, while it increases exponentially with the number of qubits. However, quantum computers have a high error rates and need to be ultra-cold, while normal computers can be used at room temperature. There is a trade-off between the number of qubits employed and the error rate. For both classical machine learning and quantum machine learning, there are different frameworks available to the public. A few of the common ones are PyTorch, TensorFlow, and Keras for classical machine learning, and Qiskit, Cirq, and QSharp for quantum machine learning. The pipeline of building, training, and testing a machine learning model is similar in both quantum machine learning and classical machine learning. A hybrid model is a combination of both classical machine learning and quantum machine learning. Hybrid models are very popular as they offer the possibility of using the advantages quantum machine learning offers while bypassing any hardware issues such as high error rates. There are different types of hybrid models. Either the data or the algorithm can be classical or quantum. In this example, we're going to have a mashup of both quantum and classical data, as well as quantum and classical algorithms. The example used in this project is the classification of quantum states. In order to accurately classify quantum states, it is necessary to generate the quantum data in a first step. The generated data can then be visualized using QTIP as points on the Bloch sphere. In a second step, the model is built. The hybrid model consists of a quantum model layer, specifically a parameterized quantum circuit layer, and a classical softmax function as a classifier. In this quantum component of our model, a parameterized rotation about the y-axis followed by a z-axis measurement is employed. For the classical component, a 2-unit softmax is utilized to learn and distinguish the measurement statistics of the two data sources. The model is then compiled with standard optimizer settings for classification. It is important to note that the classical neural network outputs indicate the network's predicted probability for each category that a given data point belongs to. In the last step, the model is trained using the generated quantum data and labels. Additionally, the performance of the model is tested on two newly generated samples, one sample point from each group. Here you can see the generated data as points visualized on the Bloch sphere. A Bloch sphere serves as a geometric representation of the pure state space of two-level quantum mechanical systems, specifically a visual depiction of a qubit in our case. Here you can see the training cost history. As evident from the plot, the cost converges rapidly, reaching a final classification error, also known as the loss value, of 0.0001034. Observe that the network assigns a high probability to predicting the correct state, despite the substantial variation in the data. The biggest setback I experienced was downloading TensorFlow Quantum. I solved that by using QBraid. Curebraid is an open source online software for quantum computing. Thank you very much for listening.